Alright, hi everyone, welcome to my YouTube channel City of Electrons. So in this video we'll be talking about the subtractor. The previous one we talked about the adder, the full adder and the half adder, and in this one we'll be talking about the subtractor. Now the process, the steps we use in obtaining the logic circuit for the full adder, that's the same step here for the half adder. So but the thing is, that's the same process for the subtractor. Okay, so a subtractor is just a digital circuit that does subtraction operation. That's it. Okay, so where we have things like this, of course binary, okay, and say this, okay, so of course this is 1, okay, that's the answer. Okay, so a digital circuit that does things like this is known as a subtractor. So we have the full subtractor and half subtractor. So for a half subtractor, it subtracts a single bit binary value from another, which is also a binary value, okay, and produces a difference, which is also a bit, and then a borrow. So this is it. Okay, A, we subtract B from A and we get this as the difference, which is the output. We also have a borrow out. Okay, so if you subtract 0 from 0, of course your answer is 0. We didn't borrow anything. And if you subtract 1 from 0, well, we'll have to borrow. Okay, that's just like saying, let me zoom in, or we can just use this side. So if you subtract 1, here the A is 0 and we have 1 as B. So if you subtract 1 from 0, we have to borrow 1, because can't move 1 from nothing. I have to borrow 1, and when we borrow 1 to this part, it becomes 1 0. Okay, it becomes 1 0. So we borrowed 1. Here it is, we borrowed 1. Then when you subtract 1 from 1 0, what you have is 1 in binary. Okay, so our difference is 1, but we borrowed 1 to make that difference. Okay, now next one, 0, we remove 0 from 1. The difference is 1, but we didn't borrow, nothing was borrowed. Okay, and now remove 1 from 1, the difference is 0 and nothing was borrowed. So this is it. So we just go for the K-map like the previous videos we did with the adder. Same process. Okay, so the difference in the logical Boolean expression depends on the particular operation. So just follow the same process. The logic circuit or Boolean expression which will show itself when you follow the process. So we have our key map here. Have our key map here. Two inputs, A and B. So here A is 0 and here is 1. Here is B is 0. Here is 1. So where do you have this? K map is for D. Okay, so D, we have, when it is 1, we have A0 B1. So A0 B1, that's how we have it here. Then the next part where D is 1, we have A1 B0. So A1 B0. Okay, so we just take that. Of course we group like we said in previous videos. So at this point we have A naught or A bar, then B, which is this A bar B. Then this point we have A B bar, which is this A B bar. Of course this is an exclusive OR. So this is for our difference. This is how our difference will look like. Okay, and then for the K map, for the borrow out, we just have one point, which is this. A is 0, B is 1. So which is this? A is 0, B is 1. So our Boolean expression is A bar B. So here we have it. So the difference, so we have two inputs, A and B. The difference will be exclusive OR, which is this. Okay, then for the borrow out, the logic circuit will be the negation, which is the NOT of A and B. So we see we have a NOT gate here. Okay, so it's just like the other logic circuits, just that in this case the AND of AB, the A is a not not like bar, a bar, so we have to add a NOT gate to it. If you take away this NOT gate, this will be a half adder, but with this NOT gate here is a half subtractor. Okay, so same process goes to the full adder. Okay, same process goes to the full adder. So in the full adder, we do the subtraction. Okay, the subtraction of two single binary bits. Okay, but the thing is this: we have a borrow in. That's just the difference. So that's just like saying we have three inputs. So look at it in the truth table. We have three inputs: A, B, and then we have the carry in. Okay, so same process. And like I said, the shortcut to fill in your truth table, like the possible outcome: 0, 1, 0, 1, 0, 1, 0, 1. Then the next, which is the second column, you do 0, 0, 1, 1, 0, 0, 1, 1, and then the first column, 0 in 4 places and 1 in 4 places. Okay, and then you do your subtraction. So if you subtract 0 from 0, 0 of course, and then subtract 0, 0. So the difference is 0, and we borrowed nothing. So just like the similar process we did with the half subtractor, same process we do here with the full subtractor. We get our boolean, our K map for D, and we'll follow the same process, and our K map for B follow the same process, and then we get our boolean expression and then our logic circuit. Now if you look at the logic circuit, it's similar to the subtractor, just that in the case where we want to make the ANDs, the AND, we are going to use the NOT of A to make the AND, so as to get the borrow out, while for the difference we just use A, B, and B in. Did I use B in here? B in, and here I use C in. Well, it's kind of the same thing. Okay, so just to change here and put B there. So B in, this will be B in. Okay, while this other B in also, borrow in. Okay, so this is basically it for this guy here, subtractor. Okay, arithmetic logic unit does the addition, which is adder, and subtractor, which is subtractor. So this is, yeah, that's that. So you can check out the previous video, because in the video of adder I fully explain the step by step breakdown this thing. So you can check out those videos. While in the subtractor, it's same process, same process. Okay, same process. Okay, so yeah, and you can of course leave comments in the comment section, and then subscribe, share, and then click on the notification bell, so that when I upload a video next, you see, you get to see it on time. Okay, and then yeah, thanks for watching, and see you in the next video. Bye for now.